Assalamu alaikum everyone. So previously we've learned how to graph polynomial functions. In today's class, we will learn how to graph exponential growth functions and exponential decay functions. And this is in lesson 7.1. To start with, this is the parent function of the exponentially growth function, f of x equal b to the x such that b is greater than 1. This function is continuous, one-to-one, and increasing. And you can see the graph of the function at the right. So its domain is all real number, and the range is f of x greater than 0. And that's because we have an asymptote at the x-axis, which means my graph cannot cross the x-axis. We also have an intercept at 0.01, no symmetry and no extrema. So let's start by our first example. It says graph y equal 2 to the x. We need to state the domain and the range. So we can graph this by making a table of values and connecting the points to sketch a curve. Here we chose 5 points. Again, 3 points, choosing 3 points is enough. So if you chose -1, 0, and 1, it will be enough for you to graph this function. Plotting these points in the graph and connecting them, you will get this graph. You can notice here that this looks like exactly the parent function with the domain or real number and the range of positive real numbers, which means f of x greater than 0. Moving to the next example. It says graph y equal 3 to the x. Again, you can use the same exact way you've used in the last example, which is doing a table. But it will be much easier and faster if you use the information you knew. So we know that the parent function graph of f of x equal b to the x cannot cross the x-axis because the x-axis is an asymptote. Because of this information, I will exclude choices b and d. And then we know that the graph is increasing, which leave me with the only choice I have, which is c. Okay, now we will apply the transformation for this exponential function. So f of x equal a multiplied by b to the power x minus h plus k. Here h represents the horizontal translation. So if h is positive, we move h units to the right. If h is negative, we move h units to the left. The k represents the vertical translation. So if k is positive, we move k units up. And if k is negative, we move k units down. If a is negative, then the graph is reflected in the x-axis. If the absolute of a greater than 1, then the graph is stretched vertically. And if it is between 0 and 1, then the graph is compressed vertically. Let's see the first example. We need to graph the function y equal 3 to the x minus 2, and then state the domain and the range. We can use the table that we've used in the previous examples. Here we have more points. And because I have 3 to the x minus 2, I know that minus 2 is my k. And since it's negative, I know my graph will go 2 units down. And this is exactly what we can see here. So the parent function had a y-intercept at 0 and 1. While now, the y-intercept moved 2 units down. And now it's at 0 minus 1. We have the domain to be a real number and the range y greater than minus 2. So I want you here to notice that y greater than minus 2. So the range here depends on my asymptote, because now I have my asymptote became minus 2 instead of the x-axis. Let's see our next example. We need to graph the function y equal 2 to the power x minus 1. So here I have a horizontal translation by 1 unit to the right. And again, here the table. By graphing it, I will have this graph. Again, our real number is the domain. And here my range is not affected. It's still the x-axis because I had only a horizontal translation, but not a vertical translation. And this is an example where you can see the parent function, f of x equal 2 to the x, and its vertical translation by 3 units up, and 3 units down, and the 3 different graphs and the 3 different asymptotes. And you can see that the asymptote depend on the k. Moving on, so now we need to graph the function y equal 2 to the x minus 4. Again, here we will use the idea that in the parent function, we had the y-intercept to be at 0, 1. And now, because of the vertical translation, it moved 4 units down. So now my new intercept is 0, minus 3, which will make my answer to be C, because I have this to be the intercept. Next, graph the function. We have here a vertical translation 3 unit up and 2 unit to the right. And this will leave me with A. Here we have a real world problem where we will use the exponential growth function. And whenever you want to solve such a problem, we always have to model the function, the exponential growth function. So in 2006, there were this amount of people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. So from the word growing, you can know that the initial amount of people is increasing over time. And since it's increasing, then I will model an exponential growth function. So we need to draw a graph showing how the number of users would grow from 2006 to 2016 if that rate continued. So first of all, you will write your givens. So initially, I have A, and this is the symbol for initial amount. So A is 1.020 in billions, and R here the percent of increasing amount, which is 0.195. So usually we model this by y equal A, and then opening a bracket, 1 plus R, the whole thing to the power of t. Since my R is 0.195, and by adding it to the 1, you will end up with 1.195. So now this is the function you have. And I need to graph this function for different values of t. We can use a table as we've done before. This is the graph we've got. Next, so till this part, we were discussing the exponential growth function. Now we will discuss the exponential decay function. It's the same exact function. The only difference is that now b is between 0 and 1. Again, it's continuous 1 to 1, but now it is decreasing and not increasing anyone. Domain is all real number, and the range f of x greater than 0 again, because the asymptote is the x-axis. And we have the same intercept, which is 0 and 1. And this is how the graph will look like. Let's see our example. It says graph y equal 1 over 5 to the power of x. Because here 1 over 5 is between 0 and 1, then we know that we're graphing an exponential decay function. Again, we're going to use a table to graph it. And then this is how the graph will look like, which is again similar to the parent function. The domain is all real number, and the range y greater than 0, because I have an asymptote, which is my x-axis. Our next example is y equal minus 4 multiplied by 1 over 2 to the power x minus 1 plus 2. And we need to state the domain and the range. So we know that we're going to have here my k is 2, which is positive. So I have a vertical translation 2 units up. And since h is 1, I have 1 unit to the right. Since I have a negative beside the 4, then my graph will be reflected along the x-axis. And since my a is 4, which means it's greater than 1, then my graph will be stretched vertically. And this is exactly what we said earlier. So this is the graph. And this is how it will look. So again, the domain is all real number. However, since our k here is 2, which means now I have an asymptote at y equal 2, then y is less than 2 for the range. So my graph is such that y is less than 2. This is my next example, y equal half to the x. We know that this graph for this function will look like the parent function. And we know some characteristics of the parent function, such that it is decreasing, such that it has an asymptote at the x-axis. And these actually eliminate this one, eliminate this one, eliminate this one. And we're left with A as the answer. Okay, similar to the exponential growth function, the exponential decay function also can be used in real world problems. And again, whenever we have this kind of problems, we need to model the exponential decay functions. So the pressure of the atmosphere is 14.7 at Earth's surface. It decreases by about 20% for each mile of altitude up to about 50 miles. Draw a graph to represent atmospheric pressure for altitude from 0 to 50 miles. So initially, I have 14.7, the atmosphere pressure, and then it decreased by 20%. From the word decreases, I know I'm dealing with an exponentially decay function. And so now when I want to model my function, I will model it in this way. So for the growth, I will have here addition instead of the subtraction. But since I'm dealing with decay function, so this is how I will model my function, where here A is the initial pressure, and R is the percent of the decrease. By putting them, you end up with this function, and now we need to graph it for different t. And this is the graph we get. In part B, it's the same exact question. The only difference is that now they want you to estimate the atmospheric pressure at an altitude of 10 miles. So now they want you to estimate the atmospheric pressure when your T is equal to 10. So we use the same equation from part A, but replace T with 10. And then using your calculator, you will end up with 1.58. So the atmospheric pressure is at an altitude of about 10 miles will be approximately 1.6. Thank you.